Hi all, this is Mr. Yeager for Honors Chem. I am finishing up the mole unit with empirical molecular formulas. What is this referring to? We are working on basically being able to identify a compound that you might eventually, in your position in your job, trying to determine what it is. Okay, this is something that would be used in forensic chemistry and environmental chemistry to basically figure out what was present at that particular scene, and then we could try to figure out what caused it, where did it come from, etc. Okay, and so what we got going on here is, especially with covalent compounds. In covalent compounds, we can have many compounds that, if I look at the ratio of elements, they all have the same ratio. All right. Remember, with covalent compounds, we didn't reduce them down to the lowest whole number ratio like we do with ionic compounds. So you have examples like C2H4, C3H6, C4H8. They're all 1 to 2, 1 to 2, 1 to 2. Okay. If we do percent composition on these compounds, we'd find that they all come out the same. So that doesn't help me identifying exactly what they are. So what do we do about that? Okay. How can we tell their difference? So what we have is we have what's called the empirical formula and the molecular formula. The empirical formula is the lowest whole number ratio of the elements in the compound. In other words, what would the compound be if I reduced all the elements down to their lowest ratio? Okay. Again, covalent compounds can share the same empirical formula, but they're not the same compound. What happens is they all have different what are called molecular formulas, over on the right-hand side there. Molecular formulas, which is then the actual formula for the chemical compound itself. All right? So the empirical formula can help us create the molecular formula. If we know the molecular formula, we could easily figure out the empirical formula. But when we do analyses, we usually get the empirical formula first and then need other information to help us get the molecular formula. So how does this work? Okay, figuring out the empirical formula. All right, what you're going to be given is either percentages or mass. All right, at the beginning of the problem. You basically do the same thing on both. We just kind of add this little step in there where if it is percentages, we simply just change those into grams. Okay, so if you have something that is 12.5% carbon, we would say it's 12.5 grams of carbon. We just change it over. We do this because we will assume, if you're given percentages of a compound, that you have 100 grams of it, so that's clearly then separates everything out nicely. If you're already given the mass, just go straight to step number 2. Step number 2, convert the mass to moles. Convert the mass to moles using molar mass. And the nice thing is, this is the molar mass of just the element itself, so there's nothing too special about it. Okay? 3, this is one of the steps that people then make a mistake on. Okay? What you then do is, after you have your list of moles of your different elements involved, you find which element has the lowest number, the lowest mole value, the lowest value of moles, okay, the smallest number essentially, okay? What you'll then do is you divide that number into all of the elements, and we're going to hope that everything comes out the whole number values. It usually does, and we'll do examples in a moment to see that. It usually will come out the whole number values, all right? What those whole number values, if I skip to number 4 before I go back to the exceptions, what those whole number values represent are the subscripts for the element in the empirical formula. So then you can just write the elements, write the subscript, the number that you got, and you're done. And you got your empirical formula. All right? But you divide all of them by the smallest number. So clearly, if you're dividing by the smallest number, that element will be 1 because it's dividing by itself. But then the other ones, you're hoping for 2, 3, 4, 5, 6, 7, etc. values. But it is very possible that we can run into some exceptions here, especially the 1.5 and 2.5 values. What happens there is you go through and then multiply all of your values by 2 to get whole numbers. All right. So in other words, let's say you have a compound where there's C and it comes out to 1, but then H comes out to 1.5. Okay. This is after you divide, you convert to moles and then divide all of them by the smallest number of moles. What you do is, clearly you can't have a compound that's CH1.5. That's not allowed. So what you do is you go through and multiply both of the elements by 2 So now you'd have a subscript of 2 for carbon and a subscript of 3 for hydrogen. So your empirical formula would be C2H3 is what you're looking at there. All right. So that's where we go. That's where we could get some exceptions. Other ones include when if you get 0.25, you multiply all your values by 4. If you get 0.33, you multiply all your values by 3. Okay? So that's where we run into some of those examples. There's more. With molecular formulas, there's not a lot of steps in this. Molecular formula, step number 1 is find the empirical formula. That's the more difficult part. Okay? Even though I see a lot of people mess up with molecular formula too. So you find the empirical formula. When the problem says find the molecular formula, the problem has to give you the molecular formula molar mass. So that will be given to you in the problem. It'll say the molar mass of the compound you're trying to find is blank. What you do is you find the empirical formula molar mass, okay, and then you divide the molecular molar mass by the empirical molar mass. This should give you a whole number value. It should come out to a nice whole number. Okay? And so all you then do is you multiply all of the subscripts in your empirical formula by that whole number, and you got your molecular formula. All right? So let's do a couple examples so you can see how this kind of works out. All right? So let's start with just empirical formula, even though this is part of molecular formula too. So what I have here is I have 2 elements, nitrogen and oxygen, and it gives me them in percentages. So what I would do is I just change those percentages to mass. So instead of 34.4%, it's 30.4 grams. Oxygen, 69.6 grams. I'm going to divide nitrogen by its molar mass of 14 grams per mole, and nitrogen by 16 grams per mole. Okay? And if I do that, sorry, I get my calculator out, I get nitrogen comes out to 2.17. And oxygen comes out to 4.32. What I then do is I divide both elements by the smaller number, so 2.17. So nitrogen comes out to 1, and I can see basically, I'll get the number, 4.32 divided by 2.17. This comes out to 1.99. So what does that represent? That's 2. So what do I then do? My empirical formula is NO2. I'm not saying that's my molecular formula. My empirical formula is NO2. And I'm done. That's it. So divide by molar mass, divide by the smallest number of moles, and then the whole numbers you get represent the subscripts of the elements. Okay? If I do the next one here, let's just try one more. This one I have mercury is 67.6 grams, sulfur is 10.8 grams, and oxygen is 21.6 grams. Okay? If I divide all these out, 32.07 is sulfur, 16 for oxygen, 259 for mercury. Let's see what I get. So 67.6. Mercury is 0.337. Oxygen, sulfur is 0.337. And this is 1.35. So 2 of them come out to the same number, so I'm going to divide by that smaller number. That's 1. That means sulfur is also 1. And then oxygen, 0.337, comes out to essentially 4. So my formula here would be HgSO4. And what my general rule for figuring out the formula and writing the formula out is write it in order of the elements given to you in the problem. So Hg was given first, so write that first, followed by sulfur, followed by oxygen. All right? Let's find a molecular formula one. Okay? Let's try, I guess we'll go ahead and try this one. Let's try this guy. Okay? So, for this one, I'm trying to find the empirical formula, but then I want to find the molecular formula. And you can see I'm given a molar mass, 110 grams per mole. So my first step is I still have to solve for the empirical formula. So I need to find each of these. H is 5.492. And you can see how I do this, where I like to kind of organize it based on the element. So I write the element out, colon, and then write the rest. That's just my preference. So first one comes out to 5.45. I don't know where I put 2 there, it's 1.01. This one comes out to 5.44. This one comes out to 1.82. So I'm going to divide them all by 1.82. Oxygen is 1.82. I can already kind of tell what these are going to be, but I'll go ahead and solve for it. This one essentially, carbon comes out to essentially 3, with the number of hydrogen basically being the same. That's going to come out to 3. So my empirical formula is C3H3O. My molecular formula, I have to divide the molar mass of the compound, of the molecular compound, 110 grams per mole, divided by the molar mass of the empirical formula. So that would be basically 55.03. So I'm going to divide it by 55.03. I mean, I can tell that just by looking at it. This comes out to essentially 2. So what that means is I'm going to multiply all my subscripts by 2. C6H6O2. This is my molecular formula. All right? That's the process behind these. All right? The big mistakes, again, I see people generally do is they find moles and they try to use those as the coefficients, or sorry, the subscripts. They mess that up. All right? I've done that a number of times. So we want to find the moles and then divide by the smallest number, hopefully get whole numbers. So I didn't do an exact example where you solve 2.5, but if there was something that came out as like 2.5, I would multiply all of these by the appropriate number to get whole numbers and keep going from there. All right. And then for the molecular formula, divide the molar mass given in the problem by the empirical molar mass. It's possible that it could be 1. If the empirical molar mass is the same as the molecular molar mass, the two formulas are the same. All right? So, one last thing. It's very much related to that. Hydrates. For hydrates, okay, hydrates are ionic compounds that have waters trapped inside their crystal structure. All right? So they actually are solid, but there's water trapped inside of the elements themselves, of the the formula units, and so the thing still remains solid. How we know this in some cases is if I heat these hydrate compounds up, what I'll see is water start boiling out of the compound, and then the ionic compound would still be left over because it has a high melting point. Okay? But first, if I want to name a hydrate, it's pretty simple. You name the ionic compound, and then you identify the number of waters, and you use covalent prefixes, mono, di, tri, etc., and add the word hydrate at the end. So if I wanted to name these guys, the first one here would be, and usually it's a dot, I just had to put like a little O there. The first one would be copper 2 sulfate. That's the ionic compound, and then 4 waters. So this would be tetrahydrate. Okay? The second one would be magnesium phosphate. 6 waters, so that's hexahydrate. So it's pretty straightforward with the naming. The ionic, just still same rules for ionic, and then you add the prefix to represent the number of waters, and you add the word hydrate to it. Okay? So that's how we name hydrates. But how do I find a hydrate formula? It's similar to doing empirical formula. What you will do is you need to find the mass of the ionic compounds separate from the mass of the water. Okay? If given percentages, again, just change it back to mass. Most of the time you're given the masses, but if it's not, you could just change it based on the percentages. Step 2, find the moles of the ionic compound and the water. And basically what will happen is the moles of water will always be larger than the moles of the ionic compound. But you basically divide that out. You divide the moles of water divided by the moles of ionic compound, and the whole number that's left is the number of waters in the formula. So let me show you an example there to finish things up. Okay. If I look at this first compound here, I have a 25-gram hydrate of nickel 2 chloride, and I don't know what the number of waters are, is heated. when I do that, 11.37 grams of water is released. So this is a common lab. Determine the formula for the hydrate and name of the hydrate. All right. So I know I have 11.37 grams of water. My nickel 2 chloride, I have whatever's the difference between 25 and 11.37. Okay, which should be what? 13.63 grams. Okay, I believe that's right. Double check so I don't make a silly mistake. Okay, 25 minus 11.37. Yep. All right. And so then what I do is I divide each one by their own molar mass. So divide by 18. Okay, this would be 11.37 divided by 18.632. And then the molar mass of nickel 2 chlorides is 129.59. So that would, so then I divide that, 13.63. Comes out to 0.105. I divide by the smaller number into both, basically, the number of moles. I should always come out to 1 for the ionic compound. And the other one basically comes out to 6. So what does that mean? My formula is nickel 2 chloride hexahydrate. And that's how you solve for hydrates. All right? So again, it's something that you can look at this one and keep on looking through the other ones and working through them with it. You can see that you might have to subtract the hydrate, the actual mass of the whole substance, by how much water is released to find out how much ionic compound is left. But that is the process of solving these. All right? So that is everything. Good luck to you.